Alright, hello everyone. Welcome to Open Rocket tutorial. If you're either here because you're new to rocketry and want to learn Open Rocket, our simulation tool, or you just want to review and you're not that familiar with it. Alright, so here's the basis of Open Rocket. First, if you're new, you can go to the Open Rocket website. You can just search Open Rocket into the search bar. It's open here. You can download for Mac. That's what I'm on, and Windows. Other you're probably not going to use. And when you download it, open it like a normal application, you're gonna have this thing. What is this? We first can see what are the things that is made up in the first page. We have our engines, which basically I'm going to talk about later. We have the stability, center of gravity, and center of pressure. We have the apogee, velocity, acceleration, and the rocket length, diameter. And we have these things, which are you can view your rocket. I'll tell you about later. And these is the simulation tab, motors tab, rocket design tab. Now you know the tabs. We can start building our own custom rocket first. Alright. Sustainer, we press this one, which is basically the entire vehicle. First, for the normal body tubes and normal rockets, we can have first a nose cone. First, not care about this. A body tube. Right. A transitional coupler. Another body tube. And usually some fins. For example, we can have trapezoidal fins. Alright, so this is the rocket. First, if you want to rotate it like this or that, you can just do this. Very simple. The first important part, how does a rocket fly? Well, what does it need? Motors, exactly. Alright, how do we add motors to this? First, the motor usually goes on the lower part, this part of the rocket. And what we use is called inner tube, this thing. This is basically like a smaller but harder cardboard tube that can fit the motor, and we can all talk about things later. But first, after we have the inner tube, we can start our motors. And then for motors, we click which one we want, but most likely we're going to use the inner tube because that's where we're going to store our motors anyway. When we click that, we can configure our motors. Now we just list new configuration. And I'm sorry for searching up this here, but usually we have a list of these things. This is called impulse. If you haven't studied physics yet, it's like the amount of energy to stop something, basically in simple terms. But here, we'll see. We can say it as like the amount of force that the motor will like put out at a single point in time. But that's for later. First, for motors for ARC, we're usually mostly going to use F-class motors. Drag it here. These are all F-class. We have a lot of F-class motors actually, like F32, F39, F42, F51, etc., etc. And these all serve different purposes because they have higher thrust per time, but most likely they're all gonna have pretty same results if you adjust the weight and stability of our rockets. Alright, so first, for example, let's use an F42, which is very, very popular. Alright, so what is an F42 right here? You can see F42T. What does this mean? Alright. This thing is called ejection charge delay. What is this? It's when the rocket goes up, and after it goes up, it can't just land immediately. It needs to have a parachute. And what triggers the parachute from ejecting from the rocket? And that is the ejection charge delay. And that we can set our own, because for other rockets, like for example, we have F32, right? We also have different numbers of ejection, like 6. F3260 is the most common F32. When we go back to F42, for example here, AT is the most popular and common, and it's what we use anyway. Alright, now we have an F42. Now, this rocket doesn't seem very rocketable. It doesn't seem it can fly very high, right? Well, what can we do right here is, first, we have different things we can change about the rocket. For example, this is the most important part. We have the inner diameter, length, and inner diameter. Right? This is what makes up our different portions of a rocket, like here and here, but also our fins and our inner tube, and even our nose cone. So using this, we can change how we want our nose cone to be, or how long how big, how wide they can be, or what the shape. Normally this is an ogive. We can also have ellipsoid or conical. For the foam nose cones, it's usually ellipsoid, and we can just change the length of this to like be what the actual nose cone is. You can use the calibrator or the ruler to see the actual length and do it by yourself. So I'm just gonna put as an ogive right now. And this is the component material. Polyester is the most common for foam, but we also have printed our own 3D printed nose cones. And using that, we use PLA. This is my custom ones. We have 30% info, about 100% info. We're not going to use 100% info for PLA, obviously, because that would be too heavy. So it would be around 30 to 20, but depending on what type it is. And this is the shoulder that, like, basically, this nose cone has an inner part here, and we can adjust that. Like, for example, we have the length is 1, and diameter is like 1.9. Like, this is the shoulder. Basically, what goes inside the rocket. We can change it to like here. Override. This is an important part for every single part of the rocket. Very important, because when we don't know, like when we have the nose cone, we can measure it ourselves using a scale, but that doesn't give us right here. But when we measure ourselves using a scale, we can override the mass. For example, when we measured, it's like about 30 grams, for example. It's probably 30, and we have a 30-gram thing, and for weights as well, 30 grams, 50 grams, 40 grams, anything could be possible. Alright, continuing, we can see how to alter if we were going to have our custom nose cones, or like custom body tubes, custom things, like in custom positions. We can go here, and like, for example, if I want my transition to be on the bottom, which is not very likely, but it can work, you use this part to see what part you want to use. And we also have different things. Right now, to control a rocket's flight, the best thing we use is called a mass component. Here. It's like, usually we use coins or different types of metal. Everything works. And if it's not explosive, then probably it'll work. And what is here, we usually just, we can, if you want for beauty purposes, I guess, you can make like, the same size as the rocket, which is basically what we usually use. And then you can have it yourself, like override your mass. For example, if you want to have 80 grams, that is perfectly fine. And for example, look, it will go 656 feet, which is not very good for us, but you know, it can work if you want for your own rocket. And this is the placement. Basically, where do you want to put it? And this is what stability is. Stability is basically the distance of the center of pressure and the center of gravity. Like, for example, if we put it here, the farthest, it's going to have 1.77. If we put it here, it's going to have 0.7, which is not very good. The center of pressure is here mostly because we haven't adjusted like the length of the rockets yet. The rocket is 22, for example. If you just have it like 10, and then make these fins a bit better, I'll talk about it later. But first, I'll just keep continuing this. And overriding this, we're not going to override the center of gravity here, because when we can override that in the sustainer, everything here, for example. And here, continuing, if we want to build a rocket, there's two important parts. There's the centering rings for the motor. Basically, this. Okay, hold on, my bad. You just go to the lower body tube and put a centering ring, right? This is like the thing that's holding the inner tube within the motor, so it doesn't like fly out during mid-flight. And we're gonna super glue it anyways. So this is also a vital part. You can add 2 of these here. Again, adjusting here and overriding here with your own mass. And finally, for the motor is you're gonna have an engine block, which for us is called the engine retainer. So it prevents the motor from falling out mid-flight. Again, you can put it here and change like the diameter, length. All these things are interchangeable. Like, for example, we could have it like this. Now, the most important part of making your rocket fly straight and also steady, this is the fins. Alright, there's currently a number of fins you can choose from: freeform, elliptical, and trapezoidal. For example, trapezoidal, these are the things that we have control of. You can make your rocket like this. You can have different types of fins, like any type you want. If you want like very crazy, you can have like this, or go for like a rectangle, or this, like a anti-sweep wings. This all works. Material, we usually use balsa wood, but we have different materials as well for like PLA as example. Alright, fin tabs. This is a very important part. What this is basically what puts the fins inside our centering rings. Basically, we have the fins right here, right? And then this part is gonna be the fin tabs. For example, right here. If it's 17 millimeters of fin tabs, alright, fin tabs, 17 millimeters, right? For example, of this long fin tabs, we mostly want this fin tabs to be the distance between one centering and the other. I'm just doing here for example. Oh, oops. Okay. And height, I guess you can set yourselves to see like how much do you want to like reach the inside. Like for example, 17 is pretty good, or like if you want to have shorter, 15. So basically it fits inside here, snug and tight, so it doesn't fall off during flight as well. Now you know the tabs, and for fins, we have another type of fins, where if you want to create your own custom fins, we can have here going to the body tube and freeform. Freeform is basically you can create your own fins, but these X, Y coordinates are what you make. For example, I could have like 1, 1, 1, 2.5, 2.5, 3. Like this is just the coordinates of these. Basically, I have 4 things, and if you want to move them, you can move them however you want, like your own shape, for example, and you can see the stability moving with it. And if, which is not very common, but you could add another line. For example, you could add like this. Interesting type of fin design, not recommended, but you can. Anything is possible with a freeform. All right, and again, fin tabs and overriding. You guys probably should get this by now. And finally, for the lower body section, we have the parachute. Parachute. Again here, we can just override the mass and then make it how many diameter you want. For example, 24, 18 inch, pretty common for our rocket. 14 grams is pretty good. These you don't really have to care about that much. They don't really affect our flight as much, but you can add them if you want for preciseness. And finally, another thing that connects the parachute to the inner tube and the transition coupler is a shot cord. The shot cord is made out of Kevlar, and if you have some previous knowledge, you know Kevlar is basically the material used in bulletproof vests. And for example, here, the diameter, we can shorten it like that. That is a pretty solid one. Again, the entire length, override it with the weight. Be sure to override with a weight. I'm just, for example, 3 grams, but it's definitely going to be more heavier than that. You just have Kevlar, and like that. That will work very well. Right, and then basically this entire rocket, technically it's ready to fly, but right now it's not because we haven't had any like motors or weight yet. And also another really important thing is called the rail button. Usually we have a launch rail, which we 3D print and made ourselves, but OpenRocket only supports the rail buttons or launch lugs, both of which are not the rail guides we want. And basically, for these, the best you can is just to set the position of these, and then overriding with the weight to be very accurate for your rocket build. Alright. Next, if we want to fly it, alright. This is not very accurate right now. It's 1,500 feet because I haven't had any weight. It's only 300 grams. Most likely for a rocket, probably 500 grams, around that, or about a bit more, like 550. All these are possible. Right? This fin is getting get a pretty average design. 1.76, pretty good. See, it goes 917 feet. I wouldn't say that is too accurate, but this is the problem. It's called coefficient of drag. Basically, the drag that is in the air. If you learn physics honors by now, then you probably know what this is, but if you haven't, then it's alright. And then center of gravity. Basically, you can use a string or your hand finger technique to determine what's the center of gravity of the entire rocket by balancing it on one finger on one spot. And then this is from the top of the rocket. And then, for example, I can have my own center of gravity. This is not very accurate, but example, 10 inches. I have 2.3 stability with this. Alright. And then the coefficient of drag. Basically, coefficient of drag is like what the friction is going to be for the air resistance, because this is for the drag. But for example, it's not going to go over 1. It might be like around 0.7, 0.8, anything, 0.9, either is possible. A good way to first look at everything right here is pressing tools and then rocket component analysis. When we go to drag characteristics, you can see our total coefficient of drag. Not the most accurate, but you can calculate it during your first flight of your rocket, and then just a test flight, for example, and then override yourself here. You can just do here. Never mind, it's 0.576. I didn't override it, but 0.576 is our supposed coefficient of drag. Still going too high, but I'm just saying for now. And finally, the final thing you should know about Open Rocket is called flight simulation. What this is basically you simulate your flight before you fly it. So you can know, like, I might get this flight, I might get this high of a flight. You want to optimize your weight so it goes to your destined apogee. Like, for example, we want 750 feet for this flight, for example, and we can test it. The best is to name it, by the way, like with your motor, like F42AT, and then here's the wind speed. For example, if we have 5 mile per hour wind, we use 5 mile per hour winds. We run it, and then we can plot the data like this. Plot data, and this is basically the graph. We have the altitude, velocity, acceleration, everything here, and you can see our apogee is about 900 feet, which is a bit high, but I haven't made this rocket the best yet. But usually we just have this, and then we can add more simulations, right? F42 AT, 10 mile per hour winds. And you see our apogee is a bit lower because the wind is higher and it's going to have more wind drift. We're going to have another one, 42 AT, 15 mile per hour, for example. And we have this. It's going to go even lower, but basically you can set your own simulations to know what is the optimal mass or like coefficient, center of gravity you want to set for your rocket or stability for this specific height. And this is a flight time right here. This is also very important for ARC. And this is about it. After this, you just like set more things, right? You have probably here you have an egg. You can name it yourself. Like egg plus egg protector. And it's overridden by the sustainer, but if you want, you don't have to override this. You can just measure everything, put it in a scale, and then override it. I'm just tucking this for now. And the final thing for the rocket is just an altimeter bay right here. For the nose cone, you can add like either an inner tube or just a mass component. I usually just add a mass component right here, like for example. This will be the thing that measures how high your rocket goes. And again, overriding yourself if you want, or overriding with the sustainer itself. And that is about it for the entire rocket. You have simulation, motor configuration, rocket design, everything is ready. And hope you've had a good video. Happy flying, guys!